Yeah, welcome to this talk. Thanks for having me. I'm excited to talk about something I'm passionate about. So, who am I? I'm Cyril. I work in the contracts team at Parity. I'm concerned with compilers, contracts, like all the things contracts in general. And the work I present today is the work of our whole team. So I'm representing the entire contracts team here. So contracts on Polkadot. What does this mean exactly? Like, this talk aims to be a slightly technical presentation, but I also want to talk a bit about some of our design choices because that's also like I get asked a lot about those topics as well. So maybe let's kick it off with some history and trivia. In late 2022, around 2 years ago, like Alex and Pep start exploring alternatives to WebAssembly because we discovered that WebAssembly might be not like the most ideal bytecode format for contracts, so they explore BPF, and it turned out to also not, BPF turned out to also not be like his very optimal choice. And so they started thinking about, okay, what if we had like a RISC-V based contract bytecode? It turns out that it's actually rather surprisingly easy to do. And so in March 2023, like Jan writes this first PolkaVM proof of concept, which showed like amazing benchmarks, benchmark numbers. So we were like quite blown away, like, and this was all like completely unoptimized. And interestingly enough, out of this like experimentation, like the idea of Jam was more or less born. Like, hey, we have this VM, we can have like, we have like an efficient gas-metered virtual machine with like a deterministic stack. We can actually maybe use it for, like, Jam was the thing back then, but maybe we can use it for Polkadot in general and not just contracts. So Jam was born, which made like PolkaVM quite popular as well. And now we had this referenda, like whether we should allow contracts on AssetToop, PVM contracts. It means like EVM compatible contracts. And so I'm gonna explain now like what we have been building on to make it a reality. It mostly consists of 4 core components. So to get Solidity compatibility, we provide our own compiler. Then we need a virtual machine for this, which is PolkaVM. We also need some sort of runtime environment for contracts, and it needs to run on some blockchain, which is AssetToop. And contracts on Polkadot look more or less like this. It's it's a simplification, but so on the left, you have your contract code, can be Solidity, it can be Rust, it can in principle be anything that compiles to RISC-V. Then you compile like your code to a PVM contract blob, and then you send it on chain, and you can transact with the contracts, and they all run in Pallet Revive. So this is the flow goes from left to right, and we're gonna have a brief look at all those components. So let's start with the compiler first. Because Solidity is like the Ethereum Solidity Solci compiler, it has only an EVM backend. So it compiles code to the EVM, the Ethereum virtual machine. We kind of don't want to deploy Ethereum bytecode correctly directly for a number of reasons. So what we do instead, we compile Solidity to PolkaVM. And this works, so maybe you have seen my last year's sub0 presentation about Solang. which is a Solidity compiler which has its own front end. But this is a lot of work, and it's much easier if you just take Sol-C as your Solidity front end, and you ask Sol-C to produce YUL, intermediate representation, or even just EVM assembly bytecode, and then we take that and we compile this into RISC-V. And this is much simpler because the YUL intermediate representation it's a simple intermediate representation format. It's not as moving target as Solidity, and we can just basically ignore all the complexity of compiling Solidity into some intermediate representation. And we then directly translate lower YUL into LLVM bytecode, and then ask LLVM, which is like, pretty state-of-the-art, like industry standard compiler framework. It has decent optimizations, and we just ask it to emit a RISC-V ELF binary, and as the final step, we link it into a PolkaVM binary. And this compiler, we provide it as a binary to run on Linux, Windows, and macOS, but we will also have a WebAssembly version, so kind of like Sol-C also has a WebAssembly version, so you can run it inside Remix, etc. So it looks, the compilation process of a Solidity contract looks more or less like this. You have the code on top, then this resol binary is invoking Sol-C to compile Solidity into YUL. It grabs the YUL intermediate representation, translates it to LLVM. We optimize it a bit, and then we invoke the Pavium linker to link it into a Pavium blob, which you can then deploy. And this is all like transparent. So you invoke, for example, resol-C as you would invoke Sol-C, and it compiles your Solidity contract code to a PolkaVM contract blob. So then, the virtual machine. So where are these contracts run on? PolkaVM is a general purpose RISC-V based virtual machine. And as I said, so it's not running like ELF RISC-V blobs directly. It has a linker, which basically translates into its own bytecode format and container format, which is a bit more on-chain friendly than just executing ELF directly. RISC-V is built on an open, RISC-V is an open instruction set architecture. And PolkaVM is quite fast in comparison to other contract runtimes. So why is that? The thing which the groundbreaking thing here is that we are using the RISC-V embedded instruction set architecture. And this is important because the embedded instruction set architecture has only 16 registers, which is roughly what regular computers have. So in x86 or ARM, you have like 16 CPU registers. This means, in practice, we can just rely on LLVM to do all the heavy lifting compiler optimizations, things like register allocations, like compiling, like in WebAssembly you even have like high-level control flow you need to compile. This is not optimal if you need to do this on-chain because those algorithms are very, very costly. They are also not really possible to do in linear time, or at least it's like not possible to do it well and do it in linear time. And because RISC-V is so close to actual CPUs, the Polkadot recompiler does not need to do a lot of work. And this means the blob is already optimized. It takes little time to compile it. And so we can have like a very efficient execution and compilation times. So here's some benchmark numbers for PolkaVM. And what this does, Pinky is an emulator, NES emulator, and it executes this emulator, and it takes wall clock measurements, and so this emulator, you can compile it to a number of runtimes, let's say, and so maybe you notice, like red is compilation time, and maybe you notice there's like nothing there in the PolkaVM interpreter compilation time, and this is because it actually takes so little startup time, it's not even showing up. So what we can see here is we have the recompiler and the interpreter backend. One provides very fast execution time, and one provides very fast compilation time. This means we are quite flexible, so we will have both backends available on chain. So, and this roughly translates to if your contract does little work, you probably want to use the interpreter because you get instant execution. Like on EVM, you also just have to collect jump destinations. This is like roughly the same amount of work that PolkaVM interpreter does, so it's almost negligible. If you want to do some number crunching, it may be worth to pay for the upfront cost of compiling it using the JIT compiler. Some other interesting observations we see, like the Solana like near native VM is actually quite far from native speed, away from native, if we compare it with PolkaVM or WebAssembly. And WASMI is what we use in the WebAssembly-based contracts palette. And yeah, WASM time is an optimizing compiler, so this is like why it also produces good code, but as you can see, so it's a logarithmic scale, it takes quite some time to compile it. So now we have our source code, we compiled it into a PVM contract blob. Now we want to execute it somehow on chain. And for this, we provide Pallet Revive. It's a fork of the contracts palette, which is already heavily audited. And it provides an EVM-like runtime. So your contracts want to read and write storage and so on. So we provide a set of sort of like syscalls your contract can call into, and we will also provide a bunch of precompiles to interact with other palettes. We want to have a single runtime, which is PolkaVM. Again, it's a generic runtime, so it can support any language, actually, even dynamic ones. And with like providing two backends for like different purposes, we're also quite flexible. Well, contract authors are also quite flexible in what direction they want to optimize. The Pallet Revive also provides an Ethereum compatibility layer, because we also want to understand Ethereum transactions. Because then we can reuse, let's say we want to reuse MetaMask wallet. MetaMask doesn't like really understand substrate transactions, and by making our nodes look like just another Ethereum sidechain, we can get a lot of Ethereum, a lot of compatibility with Ethereum tooling for free. And it also provides some like convenience around the problem. So Ethereum addresses are 20 bytes in size, and substrate accounts are 32 bytes. So we are deploying this to AssetToop. So this somehow needs to work together. So we offer a mapping. We also make sure that if your contract sends away funds to some address, the existential deposit, which doesn't exist on Ethereum, is completely transparent to it, and things like this is all taken care of by the pallet. Okay, so let's talk about the AssetToop, or contracts on Polkadot. So why on Polkadot, or the Polkadot hub? So contracts are permissionless and untrusted, and this is important. So on AssetToop, we have this thing like the minimal relay chain vision. So the idea is like, hey, we want the relay chain should only really like relay messages. Like it will be sort of replaced, superseded by gem anyway, so we want to move like things like balancing, staking, governance away from the relay chain. So the original vision, I think, was to have like many system chains, like the staking chain, the governance chain, and so on. But eventually, we changed the plan, and now it more or less goes all into AssetToop, which I find is really great, because together with contracts and this minimal relay chain vision, we can provide precompiles for interacting with with all those pallets, right? With staking, with pallet referenda, and so and this removes a lot of like burdens if you want to develop on Polkadot. So sometimes, like if you want to make a parity chain, there's a lot of gates you need to go through. You could go to OpenGov. You need to write a runtime, a chain runtime, and this is like writing a blockchain is not. It's just much more work, and there's much more gates than just writing a contract, which you can deploy permissionless. So you can interact with governance or staking in a permissionless way. And now, because everything is moved into AssetToop, it allows synchronous composability. So you don't need to send some XCM call to some other chain and wait for something to return or some state to change, which is like very beneficial, because a lot of contract languages today, also like Solidity, they don't have any concept. They just assume synchronous execution inside one block, and it makes the life of developers a lot easier if you have this synchronous composability. Some like future ideas. So there's a number of like inconvenience problems we need to solve, and maybe I can highlight two things. So one is we still have scaling potential left. Also in the vertical direction, we can think about like hot versus cold accesses to improve our caching. We can think about parallel contracts execution, maybe in an optimistic way. It's kind of like somewhat similar to what Solana does, but maybe more optimistically, so you don't need to like provide all the state items you're going to access. And also we realized like PolkaVM is so fast. It's so fast to compile and execute code. Like our real bottleneck is starting to be storage, because like accessing blockchain storage is getting the real bottleneck now. And like one contract execution involves many different storage items to be read. So we kind of want to optimize into this direction as well a bit. Then what I'm also like very excited about is we unlock new use cases you can not do on any other chain. So for example, if you want to build an interpreter contract for dynamic languages like Python and JavaScript, or like blockchain languages like Move or Solana or RPPF, you can just write an interpreter contract and deploy it, and then then you can delegate call into this interpreter contract and say like, hey, execute me this Python code. So on Polkadot, we can not only have Solidity or Rust, we can have Python or JavaScript contracts. And because we are competing with WebAssembly, with like fast wasm time compilation results, you could also think of maybe start executing like number crunching algorithms, like some cryptographic algorithms, directly in a contract. So on Ethereum, you have this precompiles, and you're like very limited, like what you can do cryptography-wise. And this goes away because it's still a bit more expensive than a native host code, but if maybe this price is worth to pay if you have a privacy-focused dApp, or yeah, as an example. So we are live on WestEnd. So the Pallet Revive is developed on the WestEnd AssetToop. We expect to land on Polkadot, so it first goes to Kasama, and then we expect Q2 on Polkadot maybe. And yeah, I'm excited to see what the future with Jam brings. You can try it out now. You go to remix.polkadot.io, which hosts a Remix instance, which supports the compiler. And so you can compile a simple contract, deploy it to WestEnd AssetToop. I want to conclude this with the elevator pitch. So with contracts on Polkadot, you will be able to allow contracts in any language, blockchain domain specifics, but also like common language. We have like blazingly fast, like this Rust catch line contracts, and you will be able to do contract workloads that are like possible on no other chain. You will pay gas with either DOT or any sufficient token. So you will be able to use stable coins to pay gas. So your users, in order to interact with contracts on Polkadot, they don't even need to hold DOT. We'll support a lot of de facto standard Web3 tooling, like the MetaMask wallet. We have still scalability potential left, and all of this is like without requiring like centralized sequencers, like very beefy machines. It all like works on standard hardware, like on any standard Polkadot validator hardware. Yeah, that's it. Thanks for listening.
Awesome. Great stuff. Cyril, thank you very much. We have a few minutes for questions if anybody would like to ask one. Yay, what's up? Oh, nice.
Hi there, hello. So AssetToop currently has a lot of assets, tokens from other parachains and the foreign assets palette, the assets palette. I'm assuming in Pallet Revive there will be available as like ERC20 tokens.
Yeah, we have to think about like what interfaces we provide. And we certainly should think about, okay, we want to make it look like those like assets from the pallets. We want to look those like they were ERC20 contracts. Yeah. So like you shouldn't need to think about it.
Good, great.
Any other questions? Nice. Oh, our first casualty. Sorry, mate. Yeah. Are you okay?
So, allowing to call contracts with any token, that requires to like change the currency configuration, no? In Pallet Revive. Is that a plan to do so, or?
Yes, so we will, okay, right now I don't think it's implemented, but it's definitively we will, yeah, if you will be able to use any sufficient asset to pay. So on AssetToop, I think it's USDC and T and DOT at least. So if your chain is configured correctly and you deploy Pallet Revive, then you will be your users will be able to pay gas in any sufficient token.
But that does mean that you will change this currency configuration type to something that can also be something else than the native token.
Right now it's hard-coded in Pallet Revive. So yes, you need to have a correct chain configuration for this. Yeah. But right now it's hard-coded, but we will remove that.
All right, who's next? Yes.
So what's the current, like percentage-wise, capability with Ethereum contract, and what is the goal? Like, do we want to achieve, say, for example, 99.9% capability, or it will stop somewhere at 90% and trying to leave all the really hard capabilities in behind and instead improve it?
Yeah, so I cannot provide you with like an exact number, but I talk about like high or good amount of compatibility. I think it should be more than like 99% because we can translate almost everything from Yule into PVM bytecode. And there's things that are like inherently tied to the bytecode format. So if your contract want to load other contract code and modify it to do some weird like EVM gas optimizations, this is obviously not possible because we have like an entire like different bytecode format. So this doesn't make sense. And things like this we will obviously not support. But in the grand scheme, it's like a majority of things, especially what we've seen, like what I say, like normal dApps do that do not sound like crazy gas optimizations that are not necessary here anyways, then you should be fine. So ideally, like your dApp should compile without source code changes. That should be like the normal case we're aiming for.
Thank you. Up here. Oh, nice.
Sorry if I missed out on it. Cross-contract calls, possible?
Sure. The only problem we have is like, so Solidity contracts, they will understand the Solidity ABI, right? If you have something like Ink currently uses the Scale ABI encoding. But if Ink would change, like release a new version supporting the Revive palette and like using Solidity ABI instead of Scale, like you don't even know that you're calling into a Solidity contract from Ink or vice versa, because it's the same virtual machine, it's the same ABI, and then it's completely transparent and just works.
Yeah, I guess there will be an interface somewhere where I can view the interface of the other contracts.
There won't be any interface. You will just call it as you would call a Solidity contract.
Okay, but I'm assuming these contracts will be documented somewhere, so I can get a list of them and see if I can find some interesting ones in them to make calls on, sort of thing.
You mean pre-compiles?
No. So, like, if I wanted to do a cross-contract call, and if I need to do a cross-contract call, is there going to be some sort of like a directory of interfaces of other contracts where I can go and discover?
You won't notice that it's a cross-contract call, given like what you're calling into supports the Solidity ABI. So I think there's some ERC Open Zeppelin libraries. You can like query like what like selectors they support. So you could implement this in Ink as well, maybe.
Okay, cool, thanks.
Anybody else? Yep, good copy behind you there. Yep.
Thank you. So I'm just kind of curious, and I'm not a compiler dev, so forgive me, but I'm thinking about like tooling support for PVM, and like you brought up LLVM. Because PVM being an extension of RISC-V, does that mean there needs to be some sort of, it's not just out-of-the-box support with this tooling, there needs to be some sort of integration process? How much overhead is there with that, or like how much is involved to make that, like to get the support that we would want with something like LLVM?
What exactly are you trying to do?
I'm just curious how much do we need to do to support LLVM for the PVM? So
PolkaVM is like kind of its own instruction set architecture, but PolkaVM provides tooling. It provides a linker, which is available as a Rust library and as a standalone binary. And what you do, you compile, you tell LLVM to target RISC-V 64 embedded. And we support a bunch of like the MDA and DC extension, and you just set this as target in LLVM. And then like it emits, like it produces an ELF binary for you, and then you take this ELF binary and feed it to the PolkaVM linker. And the PolkaVM linker takes care of translating it into the internal like PolkaVM instructions. It's close to RISC-V, but it's not exactly RISC-V. And then, so it should be transparent for you.
Okay, awesome. And is this something that's already supported?
Yes, the Solidity compiler does exactly that. It compiles first into an ELF object, and then just uses the PolkaVM linker.
Okay, word. Thank you.
Awesome. Anybody else? All good. Cyril, thanks so much for coming and telling us about this.
Yeah, thanks for having me.